as well as we have demo in plan with Hongbo, and I will be conducting labs. Shubhangi will share insights in terms of how OR is the backbone and the career insights with this new lane. So without further ado, let's get started. This is today's agenda. We'll cover foundations of agentic and multi-agent AI. We'll talk about like from research to production, system design, safety and governance, and how to achieve that. Shubhangi will talk about OR as the backbone. Then we'll switch to the hands-on lab. I assume you got the instruction in terms of setting up the OpenAI API. We conducted a half an hour of office hour from 1:30 to 2 p.m. Hopefully everyone is up and running on the API setup and will be able to use it in the lab. Then we'll have about 10 minutes of break. We'll then continue with live demonstration. That will be Hongbo. And at the end, we'll discuss emerging career and research pathways. This overall lets us to wrap up. So this is almost a 3-hour of session, and hopefully you will enjoy it thoroughly. So today's session, Hongbo and Shubhangi and I will be presenting. Before we get started with AI Agent, I'm briefly introducing myself. I'm Dhanashree, and I have been working in AI ML lane for about a decade now. I have experience in building and production deploying AI models, as well as Gen AI for Fortune 100 companies, as well as big consulting companies. So currently, I'm pursuing my research interest in neurosymbolic and agentic AI. So I am wishing that I'll be able to impart some decent insights that you will take with you at home. What is an agent? An AI agent is an entity that uses a large language model to reason through a problem, plan a sequence of steps to solve it, execute and iterate on that plan, and often with the help of tools, APIs, and external systems. So essentially, agent goal plan action alignment is very much necessary. So every agent receives an assigned goal, and mostly through a human or user input. It in turn then plans steps and then acts to accomplish the tasks given to it, and the alignment between the assigned goal by the user and the plan that it charts out for itself or other agents, they must be coherent in terms of a sequence of steps determined and which agent will accomplish what task. So this alignment is very critical. Misalignment, if any, in terms of agents drift or say token bloating, they produce irrelevant conflicting results. So LLM-driven agents can go off-rail if goals conflict or if data is inconsistent. So moving ahead with how the anatomy of an AI agent will look like. So AI agent is a computational entity that autonomously perceives its environment through user prompts, APIs, sensor data, or databases. It maintains an internal state. So it does have memory of context. It does have goals, which are assigned to it at the coding level. And it does keep track of certain past actions. Now, there are ways in which every few days of frequency, the enterprise agents are wiped out in terms of what memory they hold or what context they had, just to preserve their agility or time of throughput. We'll talk about it in more detail in subsequent slides. User reasoning, planning mechanisms, like they are necessary to decide for an agent as to what to do next. So They will do prompt chaining, and they will use symbolic logic or search algorithms. Agents will also take action, and the actions will look as if like they are doing web search, they are doing database queries, simulations, and calling another model. So this is where the agency lies with the agents in terms of like which action they would want to take in the purview of available tools, and eventually completing the task. So at the end, once these steps are executed, they receive feedback in terms of success or failure of the actions and adapt iteratively. Here comes the system of another agent being the judge of the task agent's work accomplished. So this is a high level autonomy. Just to note over here, if you have any questions during the session, please do type them in the chat. Each of us will be taking the question probably at the end of our respective sessions, or in the dedicated time we have for Q&As. So here we go with the anatomy. The agent system architecture, high-level core building blocks are planning, tool use, reflection, memory, and multi-agent collaboration. So agent decomposes high-level tasks into executable steps. They call external APIs or solvers or web search to augment reasoning. Interestingly, a couple of months ago, Google published data in terms of how agents from different agentic systems are placing calls on their search engine, and how agents placed calls, search calls look like in their internal database. Then once the tool use is completed and the output from the tool is extracted, the next step is reflection, like extracting all the outputs and putting them together, detecting errors and iterating or improving them. The another building block is memory. It tends to maintain working context short term and a knowledge base which is long term. So every agent can be programmed so that they can keep short-term notes of the learnings that they had during performing the tasks and generalizing the response, and the long-term knowledge base and learning. So if instructed well, the agent can cache the responses, certain important responses, and cache certain important learnings that they have achieved during the execution. We have one multi-agentic collaboration lab. I would ideally go through the one lab which is very foundational, and we'll see if we have enough time to reach to the multi-agentic collaboration lab, but you have the access and you will be able to execute it at your time. So this collaboration involves specialized agent. It has planner, executor, verifier, domain expert, and they coordinate through orchestration. The orchestration layer can or cannot be deterministic, meaning you can design the orchestrator as an agent who has the agency to select which tool it wants to use, or you can specifically design an orchestrator as like static one and instruct it to use certain tools in order. So both make for good agentic system, and we have use cases for both kinds. Moving on, when do we use AI agents? Now, this is a highly debated topic because most of the time when agents were proposed as a tool or system, it was suggested that complex tasks that don't have structured workflow, meaning there is significant abstraction involved, yet interpretable, and tasks that have high latency tolerance, tasks where non-deterministic outputs are acceptable, and tasks that need long-term optimization, meaning like best path identification and personalization. That's the place where we intend to use AI agents. Now, why it is debatable? Because we also construct systems where uh, they uh, they make our email systems very organized in terms of say spam emails, which will never get to our inbox in the first place, or cleaning up promotional emails, etc. So that has become possible eventually with the advent of small language models, but then which are like way more cheaper to execute, as well as their throughput is better as well. But in the beginning, when we only had large language models and when AI agents as the concept was introduced, it was expected that only long horizon tasks should be executed using agents, because that justifies for large language models high cost, building and maintenance, and that justifies the optimization loop as well. But with SLMs, we can use it for any task, like as long horizon or short term for our building. But still, we would not recommend it to use for deterministic tasks. That's just not the ideal use of compute and resources. So, future outlook, multi-agent systems are the bridge from today's large language model assistants to tomorrow's autonomous digital workers and robotic collaborators. So systems that plan, debate, and act across real-world domains. These are the ones which we see in the industry today, and we'll see more of it in 2026 and 27. Moving on. Here are some real-world multi-agent system examples. So customer service and support automation. So we have how it works. So one agent specializes in understanding the customer intent. Another agent retrieves the knowledge-based document, and the third agent executes the account action. Example like resetting password, checking order status, etc. So these individual systems today are very static and mostly involves human in loop. But with agents, we are trying to automate them in a way that human in loop can be extracted from human in loop from the system can be removed, and the system will become just agentic. So why mass as in multi-agentic system helps over here? Because modular agent reduce error, make scaling easier, and allow faster updates to specific roles. Moving on, we will build, just to note here, we'll build one very foundational customer service agentic system today in our lab. I believe you would learn a lot from that specific lab. The second one is financial trading and market simulation. This is now being implemented and used in major banks. So how it works? So essentially, portfolio balancing agent, liquidity searching agent, and arbitrage agent run in parallel. Simulation environments use thousands of agents to model investor behaviors. So over here, the high performance compute angle is that it requires GPU clusters for reinforcement learning simulations and low latency CPUs for real-time execution. So essentially, GPU clusters are used for model serving as well as fine-tuning the model based on the domain data that you might have. The domain data can be finance or retail or healthcare. Over here, one thing to note that with agents, we have identified a really good tool to model systems for simulations. We did not have with the deterministic software systems we had in the past, it was hard to codify a black box simulation, which is now possible with agentic systems. Moving on to our third example, autonomous vehicles and smart traffic systems. So how it works, each car runs as an agent, negotiating lane mergers, traffic light timing, and pedestrian movement. City scale multi-agent systems coordinate fleets for ride sharing, routing, and traffic optimization. Here, the high performing compute angle is more serious because the cost of HPC defines the success of this system. And when you enable one edge device, it can be a mobile system, a computer, or an autonomous vehicle. The HPC angle changes in terms of how compute hungry each edge device and the model running on it becomes. So heavy use of onboard GPUs for perception, edge cloud compute for swarm level coordination. It happens in these systems. It's synchronizing decisions, avoiding conflicts, and optimizing group outcomes. So scalability is another aspect. More agents mean exponentially larger coordination state space, and the management of it becomes really tricky. I have one lab which enables swarm level coordination agentic system. We might not, today we do not have almost 9 hours of time to compress all the labs in it, but do execute that swarm level multi-agentic system simulation. It will be a really good learning opportunity to model systems where swarm level coordination is necessary. Healthcare and drug discovery. So one agent explores biomedical literature, which is LLM powered. Another models protein folding. Another runs simulation for molecule binding. And the orchestration agents coordinate insights into candidate drug pipelines. So impact is it cuts years of drug discovery timelines. This is implemented, and scientists are so you must have heard about the AlphaFold winning the Nobel, and how simulations were made faster, and how the protein folding were identified faster because of AI-enabled systems. So this is an emerging area, and scientists like Dr. Anand Kumar are working behind this lane. So worth giving it a read. Tools, how agents act beyond themselves. So what types of tools agents have at their bay, which is interfaces that extend agents' reach into the real world. So they can be knowledge access, so wiki search, web browsers, weather APIs, memory and recall, vector databases, like Pinecone, and now every other hyperscaler that we know, they are developing their own vector database because it is easier to do storing of embeddings and search of embeddings through vectors through these kind of databases, and relational databases are proving not good enough for them. So for semantic retrieval, we need them. So memory and recall are enabled through these kind of databases. We have specialized intelligence, domain-specific ML models like vision, speech, finance, and science. We have execution engines like Python REPLs, code interpreters, optimization solvers like Gurobi, Hexaly, etc. We have enterprise connectors like CRMs, ERP systems, Slack email APIs. So everything that you can wrap in the form of API and give password access to like a human, you can give password access to an agent as well. It's just that you will have to monitor the usage of that tool through an agent, at least for initial some timeline, just to see that the agent has gotten used to using the tool better without any malfunctions. So this is like a typical tool schema as to how would it look. We would be going through the lab in which we'll code a few of these, so you would have better understanding. So tools are functions mapped to real world actions. So you can think of agentic system as if you know like object oriented programming, then you can think of an agentic system better. It is essentially a class, a Python class, but with the brain of a large language model. And tools essentially are functions, but those tools can in turn be other agents or static tools like databases. So here is a syntax of writing tool just as a definition. But as I mentioned, agents can also act as tools. So over here, we have prototype, like we have standards defined in terms of how the tools at the agent level will be defined. It has name, description, parameters, properties, and there are required parameters enlisted as well. So the required parameters must be passed through the tool to have the agent use it in a better way. So that's about the schema. This I spoke about just a few minutes ago, small language models as agent brains. So when the very first commercial ChatGPT-4 was launched in November 2022, in those time, the very first enterprise level available ChatGPT had about 13 billion parameters, and now the models have gotten even larger. So today's models go beyond 70 billion parameters. Over here, when I say parameters, they essentially, so large language model inherently are made of neural networks, and the more the parameters are, the better the learning becomes. But then sometimes large language models are trained for very specific tasks, domain-specific tasks. So the language model which is trained and fine-tuned for healthcare-specific data may not be generalizing well for like doing math Olympiad kind of questions. So the more higher number of parameters in a language model, the latency requirement for inference call becomes tricky. So that's why we use small language models. They are approximately half in the number of parameters. But then you can train them better on domain-specific data, as well as they are lighter. So their compute hungriness is less. So maintaining and building them is cheaper. And like small and minor task, which does not require, say, healthcare expert level of expertise, for those tasks, like email organization, we use small language models to build systems better. This is a very good paper. When you get a chance, do go through it. Here is a multi-agent AI system architecture. Now, this is a very intermediate level architecture. We do operate there is another RL loop on the right-hand side if you are fine-tuning the existing language model as well. But then on a high level, this is how a multi-agentic system looks like, where there is one supervisor or planner agent who decides which task needs to be assigned to which other agent. We have parser agent, we have designer agent, web crawler agent, and forecasting agent. Now, each of these sub-agents, they essentially report to the planner agent, and they accomplish individual tasks. They generate the output of their individual tasks and then hand it off to the supervisor agent. The supervisor agent then collects all the responses and then provides the user with an answer. Now, here is to note that in most of the multi-agentic system, where there is a where there is like a planning agent slash supervising agent, there is a judge agent as well, which validates what collective work has been produced by these five agents combined, and then through the LLM as judge, you can enforce certain systemic policies before generating the output. Tool calling is enabled for all the agents. Many a times the agents can talk to each other in certain systems, but mostly for the initial systems that have been built, the communication is just between the master agent and the other agents. So this is the type of multi-agentic system prevalent in today's enterprises. They have access to individual databases which do store domain-specific data. So how the supervisor agent identifies task routing. So task parsing is LLM-based reasoning. So the supervisor agent uses the large language model to break a natural language goal into structured subtasks. Meaning, the example is chart the market cap of top 5 banks. So so they are broken into individual subtasks, and the agent does detect those subtasks. You will see them in the lab, how the self-detection happens. So the subtasks would be searching financial data, parsing values, and generating the chart. So agent registry or directly lookup is where all the number of agents with their respective capabilities are listed. The system maintains a registry of available agents. The metadata involves agent name, capability like web search, SQL query, summarization, visualization, etc., and then input-output format. So we have like an example entry, agent capability, input format, and output format. And we have matching logic that says supervisor matches subtask. So the best agent is, so which would be the best agent to accomplish this specific task? So keyword and semantic matching, like if I need to plot charts, then I would be calling the charting agent. Then schema matching is another way. So data type compatibility of search input, parser input, and chart input needs to be aligned and coherent. And then there are obviously fallback rules that if an agent is unavailable, reassign or retry. Every agentic system, as you will see in the lab, it has been given maximum number of steps or maximum number of tries. So say, for example, this specific agentic system has max tries as 5. So in the case where one specific agent is non-responsive or it is stuck, the agent does not continue burning the compute in the loop if it is not getting any task accomplished. So delegation protocols are assigning the task in a structured request, JSON or schema based. So example is task, input, and agent. So the task would be parse the market cap. The input will be like raw HTML from web search, and agent would be the parsing agent. So the result routing would look like supervisor collects results, validates correctness via LLM judge or rules, and parses them to the next agent in the chain. So process would be, as I mentioned, it's the conversation between supervisor and the sub agents, and supervisor and subordinate agents, and then eventually supervisor and LLM judge agent. So agent output received like once the task is done. So a specialized agent example, parser agent returns its results. So say, for example, bank is JP Morgan Chase, value is 125 billion, and metric is revenue. So supervisor agent creates an evaluation prompt. So supervisor formats a check request for the judge. That task is extract market cap for top 5 banks, and agent output is going to be 125 billion revenue for JP Morgan Chase. And question is, does the agent output match the required metric, which is market cap and not revenue? So the response of the judge can be correct, like true or false with explanation. So as you can see over here, that it was instructed to collect the market cap, but it collected revenue instead. So it is not the right kind of output expected. So in these scenarios, the judge raises an exception. It raises a flag and does not get the output sent to the user. So the judge LLM compares goals versus agent output, checks goal alignment, and then it checks format compliance, and optionally compares against retrieved ground truth. Here is an agentic orchestration layer. This is a very interesting way of putting together how the entire system is stacked. So essentially, beneath cloud, we have all the chips, and they feed to the hyperscalers like AWS, Google Cloud, Azure. And then on top of cloud, we have foundation models like OpenAI, Anthropic, and Google Gemini. We used to have Meta's open source language model, but these days, Hugging Face and others have good open source large language models. So foundation models are then fed, as in they are the next stack. On top of it, we have agentic orchestration layer. These essentially act as glue in putting together an agentic system, which has greater scale, like beyond 100. And then on top of the orchestration layer, we have application layer. So there lies all of your applications which use agentic system in the backend, but then are deployed on edge devices or otherwise, like they accomplish certain specific domain-specific tasks using agentic systems. So this framework was put together by Dr. Andrew Ng, and this was first made public in the Y Combinator talk just last year. So it's very recent as well. So the purpose is this layer provides the cognitive glue that binds foundation models, external tools, APIs, and memory systems into multi-step, multi-agent workflows. It abstracts away raw model calls into autonomous reasoning and action pipelines. So the technical operations look as follows, like task decomposition breaks down high-level goals. We spoke about this, state and memory management, tool invocation, and multi-agentic coordination. So think of it an analogy, like as operating system for AI agents is that orchestration layer. You do not require very high compute to host this orchestration layer. You can, for intermediate level of agentic system, you can very much host it on CPUs. So operating system by scheduling GPU expensive interface task, the way as an OS schedules like CPU processes. So the compute requirement of orchestration layer is just very less. It's the application layer that gets dynamic compute related requests based on the demand that individual application has through its user. So we'll briefly skim through compute usage at each layer. So as I mentioned, orchestration layer is lightweight on raw GPUs. So orchestration itself is primarily CPU bound, Python services, asynchronous task schedulers, etc. heavy GPUs indirectly, each orchestration decision often calls an LLM hosted on GPU clusters. Thus, orchestration layer scales linearly with the number of tokens consumed across all model calls. Then we have optimization needs. Obviously, whenever there arises a need for deploying GPU-like compute and making inference calls either through agents or language models, there is always optimization need, and these optimization tasks are very open-ended. I have been in place where, say for example, the inference time of a certain model was say 2 minutes, and then the model response needed to be shown on the front end just by the latency of 15 seconds, like within the latency of. So it falls onto the shoulder of an engineer to reduce that 2 minutes to 15 seconds. And there arises all sorts of techniques you would implement to compress the model, or like make use of effective cache and other techniques. So the bucket of techniques is tremendous, but then the time is finite at the production grade projects. So optimization needs require like token batching, caching, and adaptive stopping criteria to reduce GPU cost. For high throughput orchestration frameworks, integrate with inference servers like VLLMs, Triton, deep speed inference. These days, NVIDIA is making their own models as well as chips internally optimized, and they have NVIDIA NIMS and NeMo type of solutions available, so that their engineers itself optimize the internal stack, so that the enterprise engineers does not have to look into model compression and other things. They can only focus on the domain specific model that has been created. So a couple of organizations are taking care of the chip level and hyperscaler level optimizations, but sometimes it's not enough. We have application layer, as I mentioned. This is where the domain specific value is created by applying the orchestration plus foundation models to verticals. So healthcare, education, enterprise governance, decision intelligence, it's all this layer. So essentially think of this as an app store, say Google App Store or Microsoft App Store. So this is an app store, but specific to the agentic apps. So technical operation is domain adaptation. It incorporates fine-tuned models, LoRa adapters, meaning low ranking adapters, or RAG pipelines with domain-specific embeddings. We have multi-model integration. Many apps combine text LLMs with CV or audio models, speech-to-text, document OCR, and biomedical imaging. This is essentially a business logic layer. It wraps orchestration flow into enterprise-ready APIs, dashboards, or SaaS applications. We have evaluation and guardrails. So this layer uses frameworks or internal evaluation harnesses to ensure compliance, trustworthiness, and reliability. So bias detection, drift monitoring, etc. And we have latency sensitive optimizations as well. So for chat and real-time assistance, deploy inference endpoints with GPU auto scaling and auto regressive batching. For analytics and decision engines, there is a place to offload compute heavy optimization problems to HPC solvers that run alongside the ML pipeline. So it is this layer where solvers can be co-hosted with other layers of technical operations. We have discussed the compute usage of application layer, but just to give you the idea, the higher distinction is the agentic orchestration layer is a control plane that is like lightweight and logic heavy. Yes, Hongbo.
I just want to mention there are two questions in the chats.
Okay.
Before going too far, do you want to do them? Vinod asks, the first question is that for workloads such as simulation or protein folding that can be executed via existing services. What are the benefits of implementing them as AI agents instead of exposing them as APIs invoked by planning agent?
Let me choose. Okay, so this one. Is my voice up there?
Yeah, I think there's an echo now.
Yeah, maybe Hongbo others can go on mute, please.
Sorry, what?
My voice is echoing, so maybe others can go on mute. So the question is, for workloads such as simulation or protein folding that can be executed via existing services, what are the benefits of implementing them as AI agents instead of exposing them as API invoked by coordinating / planner agents? So essentially, an ideal situation where, for example, you have certain number of protein foldings to be explored in order to have like final working folding, that is the destination folding that we don't have available beforehand. So it needs to be assigned to set of agents where they can divide the tasks among themselves and operate as a simulation, and essentially get the work done by assigning say exploration task, protein exploration task, or folding exploration task to one specific agent. Then the other agent takes that output and verifies based on the ground truths that exist, and eventually validating the response. So the agentic system can operate as a simulation where once the question is given and the answer is unknown, they can come up at the end of the simulation, they can come up with the answer which can be like as exploratory as protein folding identification. So the next question is, does the planning agent operate using a predefined human-authored meta-heuristic, or does it synthesize its own meta-heuristic dynamically via LLM? Both ways are possible. So like sometimes planning agent is given like an ingrained prompt where it is instructed and personified in terms of what its tasks are, and obviously that ingrained, like that instruct prompt is given by a human only. But then within that simulation, if the planning agent stays for enough time, or if it is using very advanced large language model, then you only have to define the tasks very briefly, and the rest is taken care of. The greater quality large language model used in a planner agent, the lesser number of instructions you will need to give explicitly. Take it as an analogy as maybe there is a very sharp student and very independent who requires very minimal guidance or instruction to get the task done, versus someone like normal or average who requires like thorough task description to be able to extract the right output at the end. So both ways is possible. It depends on the strength and essentially like number of parameters of the LLMs in terms of how large an LLM is to be able to take the instructions without being distracted or with like very brief in a very brief way. So
yeah, thank you for great examples. Thank you for the response.
Yeah, let's move on. So key distinction is the agentic orchestration layer is a control plane, lightweight, logic heavy logic heavy, and it coordinates compute. The application layer is the execution plane, GPU intensive, user facing, and scales with demand. So this is the compute usage part of the application layer. We have layer-wise decomposition of how much compute each of it uses and what are the requirements. But given this session is more focused on agents, we would focus less on the compute optimization strategies here. But mostly distributed system concepts and data parallelism and model parallelism. These are three things used extensively in optimizing agentic systems as well as individual inferencing systems with any other types of models. So we have cloud as a role to provide elastic access to large-scale high performance compute clusters. The compute usage is very high. Training jobs run across GPU pods, clusters often on H100, A100 instances. Inference optimized via auto scaling, GPU pools, quantization, and batching techniques. Then foundation layer, as we spoke, compute usage is HPC scale compute clusters. Serving is GPU accelerated inference pipelines, often with quantization, distillation, and low rank adapters. Distillation is a very interesting technique. The DeepSeek models that were put together approximately in mid 2024, they were entirely working on distillation technique in which the smaller models like prompt the larger models for very specific domain related questions, and they extract knowledge from the larger models just for like very specific lane of expertise or knowledge. It's almost like reading an entire textbook versus reading the question bank. So the distillation is extracting the big textbook into a question bank, and that was the technique. Agentic orchestration layer, we have LangChain, Crew AI, AG. So these frameworks to build multi-agent systems that coordinate calls to FMs and external tools. We have light compute usage, as we mentioned. And this is how the AI stack compute flow would look like, from semiconductors to clouds to foundation model to agentic orchestration and to applications. I'll be sharing this presentation with you all, so you would be able to read it at your own time. So now the protocols for construction of pipelines. So pipelines for AI agents, especially in multi-model and multi-agent systems, need standardized protocols to define how agents / tools talk to each other. That is the communication layer. How data flows across steps, that is state or context passing, and how orchestration ensures correctness and reliability, that is controlling of logic. So the model context protocol was essentially first defined by Anthropic, and then it was adopted by Google and others for standardizing how agents communicate to each other, so that the way inputs are taken and outputs are provided from one agent to another remain coherent in the place where we are now at the inflection point where most of the enterprises are building agentic systems. So this was an attempt to standardize the process. So it is a standardization protocol inspired by LangChain, LangGraph, and others for defining contextual exchanges between models and tools, defines how memory, history, and context are carried forward across pipeline stages. The pipeline role ensures each agent or tool receives not just raw input, but also relevant context, which is conversation history, retrieved documents, embeddings, prior tool outputs, etc. And the idea is, think of model context protocol as the glue, ensuring the pipeline continuity. Example, is when an agent retrieves data, formats it, and another reasons over it. So this is level 1 standardization. We have Google agent-to-agent protocol as well. And this is another level of standardization. So what it is, a Google proposed protocol for direct communication between AI agents. It defines message structure, negotiation rules, and error handling for error agent collaborations. We have pipelines of planner to executor, and it introduces handshake style messaging. So confirmation, validation, and retries. A to A may include application semantics like retries turned into service SLAs, etc. So you can consider like A to A as for pipelines where different specialized agents need to co-own steps. Example, one agent parses invoices and another validates with accounting rules and another post entries, etc. So this is so A to A is like a language for agents, and consider MCP as the baseline construct through which that communication will happen. So ADK framework is just like we have software development kit, we have agent development kit as well. Many organizations, including Google and OpenAI and Anthropic, like whoever has built their foundational language model, they have put together an agent development kit. Most of them have common standards, but then the capabilities are different for each of them. For example, Google now has an entire stack starting from hyperscaler till the application layer. So their agent development kit is a lot more elaborate. So a framework that is similar to SDKs. Pipeline role, it makes the construction modular. ADKs often enforce best practices like retry policies, logging, error boundaries, observability, etc. So these are certain examples of how open source multi-agent ADKs or frameworks would operate, and which ones are ideal for what type. Meaning, few of them are pretty good for prototyping or research related activities, but a couple of them are only ideal for enterprise production grade applications. So if your goal is to conduct research and build simulations for your research hypothesis or problem, you use one kind, and then for enterprise grade you use another. But usually in organizations, they already have a certain vendor on board, and that leaves very less scope for developers to decide as to which ADK they would want to use. So agent evaluations. So we talked about it at length, but localizing of errors are possible, meaning that evaluation framework isn't just saying that the agent has failed in a broad sense, but it is also able to pinpoint exactly where the failure happened. So in the agent's reasoning or in the execution pipeline. So localization is identifying which component broke down. So did the goal formulation fail? Was the plan incoherent, or did the action deviate from the plan? So LLM judges can mark specific failure steps. Example, say plan was logically inconsistent versus execution was inefficient, instead of just labeling the entire outcome is incorrect or wrong. So this framework has come out of Snowflake, and their research show that strong agreement with human annotations mean that step-by-step error tagging by LLMs matched closely to human evaluators validating the method. So look, this is an example as to how localized error detection and agent would work. So here is, I have built a graph for that. So agent reasoning steps. So the goal given to the agent was retrieve the average temperature in New York City for the past 7 years, for past 7 days. Now, agent builds a plan for itself, like searching web, extracting data, and generating the line chart. And then individually, the actions will be assigned. So web search for New York, then second would be parsing the values, and third would be generating the line chart using Python tool. So now the language model as judge would do error localization at action 2. So extracted forecasted values instead of historical values. So LLM judge tags this step as the failure point, matching the human annotation. So one thing to note that in enterprise applications, the planner judge, if the language model used behind planner judge is, say, OpenAI GPT 5.2, then the judge agent uses mostly different vendor than of the planner vendor, so that the mistake or the training flaws which enabled the planner and other agents to come up with a specific output, that output does not sound like correct to the judge, because it is also trained on, like, the language model behind that agent is also trained on the planner judges. So the usual example is planner being GPT 5.2 and the judge being, say, Claude Sonnet or Gemini, etc. So that those you don't make the judge as the same as the planner. That's the catch. And final is like observability techniques for multi-agent systems. Traceability across agents is very much necessary. We will see in the labs that I have printed like message logs, error handling and catching. So message logs are like record all inter-agent communication, including prompts, responses, tool calls, and environment updates. We have conversation trees, so store branching paths of reasoning like chain of thought at the system level for post hoc debugging, and then agent state snapshots, so capture each agent's knowledge state before and after critical decisions. So here, once you would build your own simulations eventually, you will see very human-like tendencies repeated, meaning if two agents are talking and one of the agent is not catching the question correctly, then token bloating can happen. So it's almost like the analogy that, if your conversation is not gotten by the other person, say, then a lot of resource, quote unquote, time is required to make the conversation happen. So and resource as time is wasted. So token and action level monitoring. So token tracing usage per agent to identify runway reasoning loops or inefficient interactions, action attributes, link downstream errors to agent action that cause them, like data extraction error versus reasoning error. And third one is confidence scores. So log model calculated probabilities for key decisions and actions. We have lab number 5, which enables you to build production grade agent, and it involves all the steps till deployment in very production ready kind of manner. So you will see that all these things are taken care of in the labs. So drift and anomaly detection. So like any other model, we have concept drift, behavioral drift, and like these data related drift that happen. So these are detected time to time in agentic systems as well. We have statistical alerts, so automated checks on response length, distribution shift, or unusual tool call frequencies. We'll have fairness and bias mitigation. Now, this is very debatable because if I am an enterprise using a foundational model which has ingrained bias issues, then even if I try to do like really good level of fine tuning or policy enforcement through agents, there is a high chance of bias and fairness issues remaining in the system because the nature of language model that I have used. So, individual foundation model building companies try to try to stay in line with each other in terms of the benchmarks they are beating. So it's not that one model is so good that the another model is not able to match its capability. Usually they fill the gap within the time of 3 to 6 months. So it is so if you, even if you are capturing the bias in the language model, then it's not your system, it's the underlying foundational model. But you can still do agent level audits for whatever is in your control. For if you are implementing the models to healthcare specific domains, you will have to comply for HIPAA and other policies, and those policies need to be fed like really well to the agents, either in form of the ingrained prompt or in like through like fine tuning of the language model. So check outputs across demographics group remain consistent, hiring assistant, screening agent, etc. This is just a check, but maybe not as effective one because inherently we are very dependent on the underlying language model. So putting it all together, observability and responsible AI framework. So pipeline layers would be input monitoring, agent interaction logging, confidence and drift tracking, fairness auditing, oversight agents, and explainability reports. So putting this all together, we get a really good agentic system. Lab number 5 and 6 inculcate all of these in one way or another. This is another example. We'll supply chain multi-agent system where there is planner, forecaster, optimizer, oversight agent, and then the outputs are fed to the observability dashboard. And observability ensures that we can see and trace what agents are doing, while responsible AI ensures they do it ethically, fairly, and safely. So my lane of research, that is neurosymbolic AI, neural agents are the ones who take care of the all the planning part, and the symbolic agents take care of all the policy enforcement part. So it enforces the trustworthy and responsible AI within agentic system, but that is like a very emerging lane within the agentic system. So these are certain best practices for transparency and explainability. So problem is LLM-driven agents and multi-agent systems are often perceived as black boxes since their reasoning steps, tool usage, and coordination logic can be opaque and difficult to trace. We have Hongbo's demo, which talks about this problem in a certain dimension. So the strategies are agent traceability tools, evaluation, attribution frameworks, as we talked, goal, plan, and action, and documentation and governance. So that would be necessary to build an agentic system that not only gets the work done, but also remains compliant to policies as well as other cautionary things like fairness and bias detection. So that is my part. Now I hand over to Shubhangi.
Hey Dhanashree, as we are a little over the time, so we were thinking that we'll do the small break and come back and do the hands-on, and my part would be after that. What do you think?
Okay. Did I go just too overboard?
No, we started a little late, and we also took some questions, right?
Okay.
There are 2 more questions though, if you want to take them now, and then we'll part for the break.
Yeah, we are on a we can be on a break, and I can answer the question just during the break. So
Okay.
feel free to. Yeah.
Sounds good. So we'll be back at 3:15?
Yeah.
Okay.
Okay, so the question.
I think Shubhangi's question is about the infinite regress, right? So you have a judge checking the planner and the outputs of the other agents. Now, who checks the judge, right? Maybe we need another judge to check the judge. Then who checks
No,
that
no.
guy, right? So is there like an infinite regress problem there, or
No,
how does
no.
it work?
So essentially, this is how typically in the agentic system it is designed. So planner collects all the output and then generalizes puts together the answer and gives it to the judge. Judge decides if it is correct, like the veracity in general, and then gives one feedback. Now the planner can, if it is too much off, again, the feedback can be like very subjective as well. But if it's like on factual basis, just like in our example, how it provided revenue instead of market cap, that's like a straightforward incorrect output. So that will be corrected. And within the system, these handoffs are also capped by the number of steps that you can take. For example, in the swarm-based agentic systems, they keep 6 shake hands between the judge as well as the planner, and that's the max. Post that, whatever the output is generated after the, say, 6th loop, it will be taken care of at the face value, and it will be shared with the user. You will see this in lab number 6, where the swarm-based system is built. The number of interactions between the judge agent and the planner agent is capped at 3 to 4, because if we keep that lane open, then there is a chance that that conversation might never end in certain cases. So, and the compute is precious, so are tokens, so is time, so it is capped. And the second question is, how about the knowledge state? Is it like whether LLM understands a concept? If it is, how do we know if an LLM understands it? Have it explain it to the judge agent. Here, every language model, say, for example, right now we have GPT 5.2. If you go on OpenAI's website, they have benchmarks related to each language model. And say, for example, the level of mathematics it can do, the level of chemistry it can do, physics, or any other general lane of knowledge. So usually the companies that build foundational models, they publish these benchmarks, like what is the level of difficulty our large language model can understand. And they have internally tested this well. So, and these are like very reliable benchmarks. So it is very evident through benchmarks. So we don't have to test it if the LLM understands. We'll just go through the benchmarks and pick a language model that is appropriate for the difficulty level necessary for our agentic system. So that's the second thing. Cool. Yeah, Shubhangi, all yours. I think we have 4 more minutes for the break.
Yeah. What a break, everyone. It'll be cool if you want to come off camera or like put in the chat how you find the session so far. Would allow some real-time feedback. You can add a quick line in the chat.
Yeah, and also about the setup, I see some questions on the setup. Is there a repo we should pull code from first? It should be in the instructions document, right? What all?
Yeah, no, there is no repo. So the idea is to facilitate things. The setup that we have is there's a Google Drive with the Python notebooks or the Colab notebooks in there. You need to set up step 1 is to set up the OpenAI API key, set up a payment mechanism. If you haven't, it won't cost more than a few cents for today's session. So you can just give a payment mechanism, and then what you do is like you download that Google Drive folder, upload it into your personal Google Drive, and then double click the Python notebook in there, and it'll open it in Google's Collaboratory or Colab, and then you can just run. You copy paste the key into the. You can just run it. So that is kind of very straightforward. That's the setup. I don't know if that helps. Yeah, Jasmine, if that helps answer. Is there anyone who still needs some help with the setup?
So to add, everybody should receive a meetup email with the instructions. If not, try search the spam folder if that happens. And if still you don't find the instructions, just put your email address on the chat box, and I'll forward the email to you.
I also just posted the drive once again. You can try if you have access to it.
Sure, I could do that.
Hey Dhanashree, we are starting on the labs first.
No, you can go ahead with the session. Meanwhile, I'll send the link for the drive and setup for those who
Okay.
have not done it.
Okay, then yeah, I'll start. Let me share. Do you see my screen? Okay. All right. I'll be discussing a critical convergence in AI architecture now, using operations research as the backbone of agentic decision making. As we are moving from chatbots to agents that take action, we need systems that rely more than just probability, more than just probability. To understand why this is important and why this is necessary, let's have a look at the grammar of decision making. OR provides 4 primitives that large language models often struggle with on their own. So these are the pillars of the OR that is the strength of OR that it brings to the table. First is the optimization, moving beyond good enough to find mathematical optimum, and providing whether it is minimizing cost or maximizing revenue. The second pillar is the constraints, defining the boundaries like budgets, physics, or time that an agent simply cannot violate. The third thing is feasibility, ensuring that a generated plan is actually executable in the real world. And the fourth thing is the trade-offs, navigating the Pareto frontier, such as balancing speed versus cost with mathematical precision. So, why your agent needs a mathematical backbone? That is the why do we need this? Because reliance on LLMs alone is risky in the enterprise operations. LLMs are probabilistic text generators, and many times they hallucinate, whereas OR solvers thrive on the complexity, and they provide mathematical guarantee. Mostly humans as well as LLMs struggle with multivariable and dependencies, but OR solvers thrive on them. Most importantly, enterprise decisions require why traces, why we are doing this, why certain decisions were made like that. So OR models clearly provide a mathematical rigor to that and mathematical guarantee. And that is why we need mathematical guarantees behind operating any agentic system. And how do we map OR to agent workflows? it is a you can look at it as altogether framework where the AI agent works as an translator. It gets translator between the user and the backbone. So first, an AI agent takes the input from the user, translates it into a mathematical formulation, gets the mathematically correct output from the solver engine, and then it takes that output and again goes back to the end user with the proper explanation from the solver's mathematical output to the stakeholder. So here are some of the real-world applications where they are already playing a role, the agentic systems. Some of them are dynamic scheduling, resource allocation, routing under uncertainty. So these are not the comprehensive, this is not a comprehensive list, but these are the domains that are seeing promising results from the agentic world. Now let's have a look at the comparison for these listed domains, how a pure agent versus agent plus OR, how they react. So if we have only LLMs or pure agents, they are likely to respond to the user input as in a greedy way. They are going to give a likely solution because LLMs work on the key, they work on getting the probabilistic answer, the next token, versus when we have a mathematical rigor or mathematical backbone of OR along with LLMs, we are going to get guarantees. The constraints that a user provides are going to be taken as hard constraints, and then we can guarantee global optimum wherever it is possible mathematically. So the key takeaway from this slide is that LLMs alone are not sufficient. In certain cases for smaller problems where LLMs also can find a good solution, they're okay. But for complexities, it is always required to have some mathematical rigor in the back end. So let's have a look at a use case. It is a live scenario where a logistic manager needs to have a cheapest, he's looking for a cheapest route. The manager has 3 trucks and 15 deliveries, but there are some constraints. Truck A has a refrigerator requirement because they have perishable goods, and deliveries 4 and 9 are perishable food and must go on that truck. The driver for truck B has to finish by 2 p.m. So these are the hard constraints that the LLM needs to adhere to, the agent needs to adhere to. Now let's see how this works inside the brain of the agent. What goes behind the hood? So first, the LLM works as a translator where it takes the user input and formulates that as an optimization problem. So it will formulate all the variables, constraints, the objective function of minimizing distance times cost, and then it sends that model to the engine of the agentic system, which is the OR solver. And now the OR solver takes that model and crunches some numbers, and it comes back with its solution and hands it over to the agent. Now the interpreter agent, what it does is it takes the output and translate it back into plain English to the end user. So at the end, agent response to the end user would look something like that I have generated the optimal plan and this is how the assignment would go for truck A, B, and C. Now let's look at how the prompts are provided, how the prompt engineering is done for the LLM agent, the AI agent. So we are strictly telling the agent, this is what we are going to feed to the agent, that your role is not to give the solution. Instead, you are an operations research translator. Your goal is not to solve the problem, but to extract structured data and formulate it and hand it over to the engine and get the result and submit it back to the spit it back to the end user. We'll give the input format, output format, the JSON schema for how the input should look and the output should look. And this is an example. Example input is schedule Alice for the morning shift, but don't let her work more than 4 hours. So the output should look like what are the objective, target variables, constraints, and how this whole thing goes to the engine and back to the translator agent when the optimization engine is done with its work. So having said all of that, we still have some challenges and risks when we use an OR solver along with an LLM agent. So let's have a look at what they are. The first thing is OR solvers are unforgiving. What that means is it takes whatever the LLM agent is going to send to the OR solver as the ground truth. So they are going to react to whatever has been sent to them, and they are going to provide a solution based on what model they are getting. So if there is an error in the model itself, the OR agent, OR solver is not going to correct those by themselves. So they are going to send back an incorrect, even if it is a feasible or optimal solution, it is going to be incorrect. So how do we mitigate that? So we need to have some validation loops where the agent restates the constraints, and then we send it to the end user and confirm. Then the second one is latency and compute costs. So LLMs to start with are slow, but complex maps and complex optimization problems are even slower. So what is the impact? In real-time, agents cannot always wait for a global optimum. So what is the trade-off here? So we have to have a plan B ready, where we have to have some heuristic fallbacks if the solver takes too long. And the third thing is empty set problem, where infeasibilities arrive. So mostly like users can ask for impossible. For example, deliver this in 1 hour when the drive is 2 hours. So what should we do? So the solver, if we let the solver take its course and come back with infeasible, the agent can crash. So what is the solution? The agent must be trained to interpret infeasibility signals and negotiate with the user. They can just ask, if I cannot do it in 1 hour due to traffic, is 2.5 hours is feasible? Is it acceptable? So this is what I wanted to share about the convergence of AI and OR, how the OR plays a vital role in AI system architecture. And I think we are now ready for the hands-on lab.
Thank you. Thanks, Shubhangi. So hopefully everyone is ready with the Collab notebooks opened on their browser. Let me just share my screen. They don't go in the similar downloadable drive over here. I assume you have the setup ready as like all these labs uploaded on your own drive, and you are able to open it with Google Collaboratory. Is everyone able to do that?
Yes.
I'll just be honest with you. I'm like a super beginner. Like I tried to upload the zipped file to Google Drive. So that's like the level of beginner we got going on here.
Okay. Let me quickly show how to go about it.
So I've actually gotten the first two uploaded, so that was fine. So you don't need to demonstrate that for me, but just I don't know, there may be some other people who are maybe a little bit shy about saying that they're a beginner with this, or maybe I'm the only beginner here.
Yeah, let me quickly go through the setup part. So essentially on your drive, you will upload, you will click on the new folder or like folder upload essentially. And then from your own device where you have downloaded like this folder from my link, you will upload it on your own drive so that it is accessible within your drive under the Google Collaboratory app. So usually, like Google Collaboratory is free for all and available with the Google Suite. So you would be able to open each of the lab just like this within your drive using Google Colab and run it using the API that I have shared.
Quick thing, sorry to interrupt, but is there a way that you can send out the zip file because I registered kind of late?
Oh yeah, I have pasted the link in the chat. Just
okay.
Yeah.
Thank you.
So download that zip file and then upload it on your own Google Drive and then open it with the Collaboratory. So that's straightforward. I have also shared this document and held the office hours for setting up OpenAI API. That is also pasted in the chat. So create an OpenAI API. It will look like this. So this is my first OpenAI API key. This is the second one. I'm going to use one of these for running my labs. Usually the setup for lab that we have, it will not be supported by the free tier of OpenAI. So just load it with like $5. Only like $0.02 will be used for the amount of tokens that we are going to use. And maybe eventually it will help you to build agentic systems post this lecture has ended. I hope everyone is on the same page. Is everyone else ready?
Would you mind sending the file one more time? Sorry, I think I got the API one, but I didn't get the file.
I did send it.
So it's not one file. There's a link. Like if you look at it, are you able to see the chat, Sarah?
I think my chat, I think.
Oh, okay. Maybe if you joined later, like maybe the earlier messages won't come.
Oh,
Yeah,
okay. I think somebody might have forwarded the drive.
Yeah, I didn't just posted it. Thank you, Irene.
Oh, gotcha.
Yeah.
Thank you.
Yeah. So all the files are in there. Yeah.
Gotcha. Thank you so much.
Yeah, no worries. Also, if I could make a request, like if you're comfortable, I would suggest to bring camera on so that like we can actually see the faces and it'll be more like not looking at an empty room. So if you're comfortable. If not, no worries at all. And we can also see live the reactions or if people are struggling or like what's happening. Okay, Carrie.
Also, is there a link to the slides also?
We will share that later.
Okay, I'll just give 1 more minute for everyone to settle so that I can get started and go ahead with the session. Hopefully, the billing part and everything else was straightforward for you all.
Aryan has a question.
Yes.
Yeah, I just wanted to ask, like, I saved my API key onto like a Word doc and saved that doc aside, but is there a better way to do this? Like, is there a place where we can store API keys? Maybe we have some for other applications or other users. So, some platform that we can use?
Yeah, ideally, what you do is, for example, you created one API key and then you used it today. And post today's session, I would suggest that you delete that API key and create a new one, because with the paid account, you have unlimited number of API keys that you can create. And with the creation of every API key, there is no charge. So OpenAI charges you only for the tokens or number of tokens that you will be using essentially, and not for how many keys that you will create. So it is recommended that you usually not save a specific API key for really long.
Got it. Thank you.
Cool. Let's begin. Yeah, so here is, let me open my own environment setup. I hope everyone has pasted their own API keys over here and ran the environment setup. So over here, ideally, I would convert it in an environment setup with environment variable. In enterprise grade applications, you don't expose OpenAI API keys or any API keys like these. The worst case scenario is you use it in properties file, but an ideal scenario is you hash them out, and just like how you use like driver credentials within your code, you use the API key just in the same way. So just execute this setup code and see if it is working for you. And then we'll go ahead with the very first lab, essentially. So today we have like total 6 labs are available in your packet. You can execute them at your own time, but then we'll go through like very specific ones given we have time ceilings. So this is one specific use case that has ticketing mechanism as that we are going to solve. So so we have, we'll use one hard-coded user question, and then we'll have mock knowledge base created with a subtle contradiction. In typical enterprise systems, you will just replace this knowledge base with your relational databases, your non-relational or NoSQL databases, etc. We'll create tools like search knowledge, policy explainer agent tools, and create ticket tools. These are mock tools that we are going to create within our code today. But then with the advent of agentic systems, tools are available with open APIs that you can access directly, like say search tools for say airlines or hotels. These are available through like links for certain platforms, and then you can embed them within your code. But for the ease of understanding, we are building them in the mock level today. We'll have the orchestrator call tool. We'll have agentic loop, where we'll make multiple tool calls. We'll have JSON decisions, and we'll have rich logging plus debugging as an output. We'll have final user-facing answer over here as well. So this is our second lab, tools done right, agent, and we are using agent as tool in a ticketing flow. So consider a scenario where explain New York City Art Museum policies, and based on the visitor's question, create a ticket only if there is an actual contradiction in the return policies. So here it will be a user-facing agentic system that we intend through this code. And essentially, we'll create a knowledge base of New York City's museums policies, and we'll give certain scenarios in which policy contradiction exists. And if such contradiction exists, then the system or the code base will generate a ticket. And if no contradiction within the policy exists, then it will simply give the answer just like a normal chatbot. So what creating a ticket means in this lab is in enterprise agentic system, support, compliance, risk, HR, ITSM. A ticket is created when the agent detects policy conflict or detects a process violation or finds information that needs a human review or identifies a gap or inconsistency that requires escalation. So in other words, a ticket is equal to an escalation pathway to human for intervention. This mirrors real world systems like ServiceNow, which does incident management, Jira issues. We have Zendesk and Workday cases for HR and compliance. So we simulate that pattern in this lab. So when will be the ticket be created in our agent? So in this lab, the ticket is created only if the policy explainer sub-agent detects a real contradiction in the written policies. A contradiction means that one policy explicitly says that X is allowed and another explicitly says that X is not allowed about the same object, like bags, luggages, backpacks, etc. So the example contradiction is, say policy A says large backpacks are allowed if worn on front, and policy B says that backpacks are not allowed and they must be checked because these conflict directly, and a human should review like what are the nuances which are not apparent for a chatbot through a created ticket. So here you will run with me parallelly, install and set up the OpenAI thing. So we are doing pip install, we are importing JSON, we are importing OpenAI. Just paste your API key over here and run this cell. We'll have an optional API test over here as well. Currently, we are going to use GPT-4o Mini, and the input will be a quick test. We'll replay with like ready for lab 2. So this is going to be our easy client response. You can replace this with greater or heavier models like GPT 5.2, but then the token cost is different for it. So once you will get to see the entire model catalog by OpenAI, you will see that there are many flavors of models available. Some are good at math, some are good at reasoning, some are good for like healthcare specific related use cases. Some are just like very small language model, just like 4.0 mini, and it is able to encompass like very average human level tasks as such, like someone who is a museum keeper per se. So the better model you use, the sharper it gets. So hope everyone has executed till this point. So visitor question, it is hard-coded for now. You can have your own question. So participants are free to change the question and make it contradictory or aligned with museum policies to attain the agent response. So this is going to be my question, that I have a big suitcase with me and I'm traveling based on the NYC museum policy. Can I visit the museum with a suitcase? So this is a very straightforward question. Now, for building the system, I'll have to create the mock policy knowledge base. So my knowledge base is ID, title, and text. The title is general visiting policy and text is the content. For example, like visitors may bring small backpacks into the museum as long as they are worn on the front, and food and drinks are not allowed inside any gallery spaces. Then bag and coat check policy, and then third one is photography policy. So backpacks, large bags, and luggages are not allowed, and small bags are allowed. So these are like the straightforward ones. Here, the third is retrieval and ticket tools. So here these are my tool functions, where the first one is search knowledge. This is my attempt to build like a low-level retrieval function where it returns policies that contain any word from the query. If none match, then return the whole knowledge base to keep the demo flowing, meaning that it is going to match the words semantically from the user question to the title of the policy and text and title of the policy, and see that which policy it needs to look up essentially to even to give the answer. So this is my search knowledge base. And the second one is creating the ticket. By default, the ticket priority will be taken as medium. And by default, I mean, if the default is not set, then like typically the agent decides what is the level of priority for the ticket, high, medium, or low. And here, this is a way to generate like ticket ID. It is like hashing a certain title plus description. In more relational database and non-demo kind of places, usually they have their own way to build new IDs, new ticket IDs. So you can just directly call those if you are building such kind of tools. So we have a policy explainer sub-agent, which is agent as tool. Here, this is the agent. When we build an agent, we are giving some agency. So the policy text will be taken by this agent, and then it will also take the user question. So it is the sub-agent that explains policies and looks for contradictions and returns both the explanation and a machine-readable verdict. So we are using GPT-4o Mini as this agent's brain, and we are going to first define the agent's persona over here. So and that is done through the prompt. Like you are a policy explainer agent for an NYC art museum. And here is the combined policy text. So the policy text will be retrieved from the knowledge base that we have created, and a user's question will be passed through directly where the user question is captured. So over here, we are hard coding the user question for ease of understanding, but this can be directly embedded in a CRUD system where you are retrieving the user question from the front end. So we are instructing the agent what are going to be its tasks. So we are explicitly mentioning the goals. Hongbo is yawning. So you should execute the file. So your tasks are going to be explain clearly how the policies apply to the visitor situation, identify any internal contradictions or confusing parts between the policies, especially about bags, luggages, or suitcases. Third instruction is say whether there is a genuine contradiction, and end your answer with a verdict that was there a contradiction or no contradiction. In case of the contradiction, create a ticket. So this is like a simple JSON helper for model decisions, meaning if the input JSONs are not in a certain format, then this clears out those input-output formats essentially from like markdowns and things like that. So
Dhanashree, I have a super quick organization question here.
Yeah.
So here we are giving the entire policy text to the policy explainer, right? So, and then asking that. So then why did we need the function before in the previous cell for the search knowledge, where it had to kind of tokenize and reduce that? Like maybe I missed the connection.
So essentially in places, in places where giving an entire policy text is going to enhance the prompt length so much that it is beyond the prompt length that an agent can take. Yeah. In those cases, like the chunking, like breaking it down through tools, that it helps.
Okay, so if we were to use that function, then in this policy explainer agent, we would kind of make a call to that, right? So it's like, this is the user's question. Go find what are the relevant policies, and then with that, answer the questions.
Yes.
Okay, yeah, got it. Thank you.
So we'll give tool descriptions, like you have access to these tools. Orchestrator will call them for you, like search knowledge that we have created, policy explainer, It will take policy text and question, and it will create a ticket like low, medium, high. And here is a definition like calling of for tools. So we'll have name, arguments, and state. This is a static orchestrator. In many systems, orchestrator itself is agentic, meaning there lies an agency where in what sequence you want to call tools or in what sequence you want to call other agents is decided by that agentic orchestrator. You will find agentic orchestrator in one of our later labs. This is static and still very much agentic, where we'll decide in what sequence the tool call will happen, and in what sequence the answer will be generated, after how many tool calls the answer will be generated. So we have like if so orchestrator routes the tool calls to Python functions, injects sensible defaults based on current state and user question. We have tool name is equal to search knowledge arguments dot get query. So this is a place where we'll be calling the tool based on its name, and we'll pass it as a parameter. And then the last one is agentic loop, where it thinks, it breaks the tasks, and it calls the tools and finalizes the answer. So its mission is explain NYC Art Museum policy that apply to visitors question and file a ticket if a genuine contradiction is found in the return policy. We'll define its states. So a current agent's state is defined by how much knowledge is fed to it. Here it is through policies, policy analysis, and the ticketing mechanism. Here maximum steps is 5. So for example, it is trying to call the knowledge base tool and the knowledge base tool is not responding. Then after say 5 attempts, it will abort and it will return an error message that a certain tool is non-responsive. Or in certain cases, if we have instructed the agent to generate response anyway, regardless of if one of the tool has failed, then it will essentially return the response without using that input. But here we are not using the other mechanisms that I described. Here we are capping the attempts. So again, like in the agentic step, we are explaining as to what all agent will be taking. So it will take user question, it will take mission, it will take tool descriptions, it will build its current state using policy retrieved, analysis done, and then if like there are any tickets created, and then the recent tool errors, if any. There are guidelines that we give to the agentic prompt that you must call search knowledge at least once before choosing the final one. Use policy explainer to analyze the policies in the context of visitor's question. Only call ticket if the analysis clearly indicates a real contradiction. Now, one thing is to understand that it is vital that you define your agent correctly with the guidelines. But then again, those guidelines are also can also be like as verbose as they can get or as succinct as they can get. So defining or personifying an agent and enabling it with all the instructions, guidelines, and tools is also an art. So not necessarily all engineers or data scientists master it in the first place to give the correct kind of guidelines to extract the right kind of response. So building a system with a likelihood of non-deterministic outcomes, because you are defining agentic personas here through guidelines just here, and there the human intervention is here, which again paves the way for errors in like describing guidelines in itself. So that is why we need to be very cautious in defining agents and building non-deterministic systems in general. So over here, once you execute, like calling through the orchestrator, and it will search through the knowledge, and it will log if at all any knowledge base not found or any interim errors are logged, and then it will return you the decision as to what were the retrieved policies, what actions were taken, in what sequence these steps were executed, etc. So hopefully everyone came till this point by executing, and at the end it has retrieved policies based on the code that we have written, and it has parsed the decisions through the tools that, like, it has gone through the policies and it has searched the knowledge base in terms of like what was available through our knowledge base in general.
Sorry, Dhanashree, I think I missed where that judgment kind of piece happens. Like, so I understand the loop, right? So we first go through the loop and like create this and run the first query, right? In the LLM, and it comes back with the output. And where is it that it kind of says what is the what is like the next step, right? Like, should I continue with the next step, do something else, or like terminate, right? I see the break statement there, but I didn't really see where it gets the action getting set to final or not.
So as we have decided for it to be capped at 5, so the loop will inherently run for 5 steps in turn, and if in the first go the outcome comes, then it will generate it, and if not, then it will keep repeating these steps in the loops that we decide. So you will have to do certain debugging over there itself, because I have written like very dense code, so won't be able to like pinpoint just at the moment. Yeah.
Okay.
Yeah.
Okay.
So till now it has parsed the tools and then eventually has retrieved policies. It will go ahead and this is the specific ticketing mechanism where it will take the visitor's question and retrieve policy, as you can see. If the current state of the agent is not cleared, then it is likely that the policy iteration can happen in how it has happened right now. So for example, I have run this code for 5 to 6 times before, and the state of the agent now is defined by like the previous iterations as well. So it goes through all the previous iterations in the current one, because they are not wiped out from its state. So, and hence you are seeing multiple loops over here. You can dedupe them within the code, but that is not always necessary as such. So we'll have a final user-facing answer where it will, in places where if it has found a contradiction, then it will mention that in specific which policies the contradictions were found. So let's go to the user-facing answer. The question that I had given was, I have a bag, and if I can like travel to the museum. So here the bag related policies were very clear in the knowledge base. So no ticket was created because there was no contradiction found. Essentially, regarding my suitcase, I'll need to check my suitcase at the museum, as large bags and luggages are not allowed in the galleries. So applicable policies are the bag and coats check policies, and it will also mention what were the applicable policies were, and it will also mention based on our previous print statements if at all any contradictions were found. So why no ticket was created over here? So policy one was visitors may bring small backpacks if worn out, and two were for the allowed with certain rules. So over here, I have explained it at great length in terms of where the contradictions were found based on the knowledge base. We'll go through a specific example where there is a deliberate contradiction introduced within the lab, and there it will decide for itself and generate the ticket. So contradictory policy snippet is below, and we'll update our knowledge base with it. So in which the sentence one says that luggage not allowed, and the sentence two is saying the luggage is permitted. So we are introducing this one that backpacks, large bag, and luggages are not allowed in the galleries and must be checked. And second is, however, luggage and roller suitcases are permitted. So here there is a contradiction, and probably there is a human intervention required. So example, the user question that will trigger a ticket for sure. You can make your own questions and see as well, but this one triggers as tested. So this specific one will trigger because the user explicitly referenced the contradiction. The updated policy text actually contains the contradiction, and the sub-agent or policy explainer agent is designed to detect lines like verdict or contradiction found. So the main agent loop checks for any contradiction found, and if found, it calls and creates tickets. So this pipeline will first retrieve relevant policies, detect contradiction, emit verdict or contradiction found, main agent escalations to ticket created, and final answer explains both the policy and the reason for escalation. So you can paste, so this is everything in one cell. You can just paste your API key over here, and essentially it will put together like an answer for a severity aware escalation system based on the question that you have given, and it will generate a ticket at the end. So hopefully everyone has reached up to this point. As you can see that this agent's is instructed to create low, medium, and high level of severity, and we are explaining like when to create what type of severity. So what do we consider high severity? Strong contradiction that may cause visitor to be treated inconsistently, denied access unfairly, or create legal compliance risk. So imagine in a parallel system where probably you are creating a healthcare system in which it's a triage, that it's an ER system where what kind of patients need to be treated on an emergency basis, and you can feed entire policy manuals in agents prompt level. The current capacity in which language model of decent capabilities understand and take prompts up to like 1 billion tokens. So 1 billion token is almost like a more than 100-page book. So that much it can take in terms of one-off instructions if explained within its body as such. So this is how you will define it, and you will see that within the code, the unknown verdict is given when either the agent was not able to reach to a certain contradiction versus non-contradiction kind of verdict because it did not receive the correct tool assistance, or the user question was not framed correctly, etc. So we have made an exception in what scenarios we'll go for an unknown as a decision. And again, like what all I have described before, we have put it together in one cell for like an entire severity aware detection system in just by the click of one cell with you keeping the API key in the cell essentially. So this is how if you look at the outputs at the end, you will see that let us go through the output together. So the visitor question is New York, larger roller suitcase with me. Your policy says luggage must be checked, but also if allowed, if carried, which policy is correct? And should I bring my suitcase at all? So, and now it goes through all the tool assistants, retrieves knowledge base, and at the end, it is post the policy analysis, it puts together a verdict as contradiction found and severity as high, and it has created a ticket which is for high policy contradiction about luggage and suitcase, and the description it has put together is detected contradiction in luggage policy with a certain severity, and the final user facing answer it has generated is based on the museum's policy there is indeed a contradiction, and here is what you must know, and it pastes the knowledge base just as it is, and it will give its own level of instruction which we have not instructed, but it will be based on the general understanding of large language model. So like if you need further assistant, museum staff, and enjoy your visit to NYC, so it has created one specific internal ticket, and it will have customized user response for the same. Now, just plug in and play 1 second, one severity aware escalation system where there will be not any contradiction because we are framing the user question in certain way, keeping all the policies just as the same as the previous one. So this is our like agent as tool kind of use case where the orchestrator itself is static, but then the agent goes through the policy documents and decides what answer is correct, essentially. Okay, I think we are at time. I will hand it over to Hongbo for his demo. We will, you can continue with other labs, and we'll share our contact details. If you have any questions, you can definitely ask. All the labs we have run before, and it has very good documentation essentially with problem framing as well as why a certain answer is coming and what kind of orchestrator as well as multi-agent system it builds. So it should be easy to understand and compile at your own end as well. So with that, I'm handing it to Hongbo back.
Thank you for the very comprehensive introduction. Let me share my screen here. I'm going to talk about, I have about 15 slides, and after that I'll do a live demo on my laptop. So the focus in this next part of the talk is kind of more focused on the problem I had experienced in my past work life. So by the way, can everybody see the slides, right? Just make sure. Okay, cool. Let me do a brief introduction of what got me interested in this the content, what I'm going to talk about. So I was trained as an operations researcher and applied mathematician. I did a few years in academia research about solving NP hard problems. Then about 6 years ago, I joined Meta to solve actual big production optimization problems. That's where I learned this the third bullet, the messy reality and poor OR modeler. So basically, I'm going to talk about that a bit, and And what I learned, the problems, other than designing fancy algorithms and essentially deploying the optimization model in reality. Cool. So before that, let me say a little bit kind of history that it's quite interesting to see that the history kind of repeat the same topics over and over. There was one very good article came out 40 years ago that talks about we should kind of merge AI and operations research together because those are two kind of disciplines that are solving different kind of problems. Where the main message in this article by Herbert Simon, which is the first person who won both a Nobel Prize and Turing Award. And the main message in that document is that OR is solving very structured problems. That you have objectives, you have constraints. All of them are can be elegantly written down using equations, right? And using numbers to quantify them. While AI tools are designed to apply to ill-structured or knowledge-rich decision domains. That's kind of natural that you're seeing large language models are dealing with like vague, large amount of text. So those two disciplines are never going to be replacing each other. So you cannot really think of you are using large language models to solve an integer program, and that's just insane and very inefficient. And recently there are also a lot of interest that in academia, where I have this recent paper in middle 2025 talking about merging the research of AI and OR or combining them. And those same kind of topics resurface after like 40 years. Okay, so the messy reality of putting optimization models in production. In pretty much every like organization or business that uses operations research, there are essentially four kinds of people. There's business leader that makes decisions or allocate resources. There's a business stakeholder or executor. For example, if you're doing capacity planning or doing any kind of planning or design, they are responsible for the actual output of the decisions. And you have OR modelers who is advocating that, hey, this is a problem we can solve by using optimization. Just give me time, give me resources, and let's build this awesome software, right? And also there's engineers that whose primarily focus is on like stable pipelines and the robust UIs and software solutions. So it's not so easy or straightforward to, for one thing, convince people or to make optimization actually drives the actual decision making. Several challenges comes in the shape of like data quality problems or very fast changing requirements, communication bottlenecks. People use different languages and have to sit through long meetings to get aligned. And the worst scenario is that you have a model that produces results that are not really usable, that does not really make the decision better, right? So the current solution without Gen AI is that we have people, we put time and resources to tirelessly update and test our implementations. We built a lot of data dashboards to visualize input outputs in different angles. But interestingly, you can do that, but the nasty problems usually comes when you try to intersect the different data sources. There's a kind of curse of dimensionality problem. There are problems that you cannot really surface by just looking at one data source. For example, if you're doing a planning problem to ship commodity to a warehouse, let's say you have one data source says when is that warehouse available, right? The time dimension. And you have other dimension that says I have X amount of commodity products coming into this warehouse, and we need space for that warehouse. If those two things don't match, you have a problem. But you cannot really have this problem, see this problem without putting them together side by side. And one last thing, in reality, we always end up solving a lot of variants of the optimization model itself. If the model is infeasible, we have to provide a solution. Hey, why it is infeasible? Which part of data is causing the problem, right? So if it is infeasible, we solve a relaxed version, and then it comes to the question that which constraint you should relax first. So you have to order all of the constraints and relax them one by one. That's one kind of challenge, or it takes much more time to solve those variants of the optimization. And in some other projects, we built very fast UIs to perturb the problem and try to figure out why is my solution like this, right? If, for example, if we have like a scheduling problem and the solver does something that looks very weird, then we on that UI, we could manually drag this allocation, this schedule from my solver provided solution to a solution that we think will be better. And then we have to recompute all of the metrics to see, hey, maybe there's a constraints that actually got violated if I do that perturbation, right? So this kind of engineering or solving variants of optimization takes a lot of time and efforts, and the challenge is especially becomes challenging when you have to make decisions in a very short amount of time, right? For example, in planning, you have to, have a complete plan in 2 days, and that's very stressful in business. Cool. So in the recently there's a paper coming out, and that actually does this, try to argue that Gen AI solves this problem, this human model interface problem very elegantly, and there's great potential. And it argues that Gen AI can help on these 4I goals. 4I mean the 4 of the I's are the insights, where the Gen AI can provide a trusted live view of the current state before optimization begin. It can provide better interpretability, or explain why is my solution recommended, and what are the binding constraints. And it will improve interactivity, allow users to conversationally explore scenarios, and even enable rapid model adaptation if the real world conditions change when we're trying to update our model to model those new conditions. And ideally, okay, what we really need is, for example, an agent. We call it Agent Awesome, that can kind of handle most of the questions from decision maker, from business executor, from engineers in a kind of automatic way. And we only leave the real, difficult problems to OR modelers. It also kind of streamline the whole overall process, the business process, by having the other people knows more about the optimization solver, or having more trust of the solution that it was provided. Right. That's an ideal scenario. And then in the next hopefully 20 minutes, I'm going to give a live a demo on kind of how can I put together an agent that does this, right? Well, for our agent, it sounds an awesome future, but how far away from there, and how much work we need to do to make it actually work? And what are the gaps? Is our current large language models smart enough that it can answer a lot of questions about your OR model, right? And so what I did in this experiment is I chose a public available problem that comes from a supply chain planning problem in car manufacturing. This data set and the problem setting is reported by researchers in actual car manufacturing companies in this paper in 2020. And essentially, it tries to model a supply chain that has several layers that's from the parts producer and inventory, warehousing, and assembly pipeline. And each of the node here is a kind of transportation link, right? And basically, this chart here includes 4 supply chains of the seats of cars, the batteries of cars, engines, and gears. And each link here will take some time for the transportation to finish. And on this supply chain graph, there are different products flowing. And the interesting part, or the tricky part, is that each ordered car is made up from different components. To be specific, well, each customer may try to customize their car in different ways. So you end up with, for example, engine. So one car, you need a specification of which type of engine it needs, which type of gear it needs, battery, and seats, right? So essentially, for each ordered car, you have this a tree-like structure, so-called bill of materials, and those products are what's actually flowing on this supply chain graph here. And the planning objective in that model is, for example, it has multiple things. It tries to maximize the on-time delivery. It tries to minimize cost. The cost includes both of the inventory and transportation, right? And overall, there are 30 types of engines and about 10 different types of gears and battery and seats as well. So it becomes kind of non-trivial, but non-trivial and large enough optimization problems that you can solve. That is kind of fairly close to what's actually happening in practice. So what I did is I wrote code to implement this optimization model. So on the top, you will see there's a kind of OR solver pipeline. I'm using the public solver, open source solver Skip to solve these problems, and it inputs the data sources that are provided along this paper and produce a solution file. Below that, I'm also building an AI agent that actually helps me to understand my solution and my source data better. So here, differently from what Dhanashree presented, I'm using a different framework that are constructed by built by Hugging Face company. It's a package called Small Agents, and what's special about this Small Agents framework is it's very powerful in writing so-called code agent. Here, what it does is that the output of code agent is actually executable code in your environment, and it'll try to run the code snippets that it produced, and try to figure out, okay, are we solving the user's question or not? If not, then it'll try to improve the code it generated and run it again. So here basically you have two types of inputs. The user question here may be very specific about my model, right? For example, if I solved my optimization model once, and one question I can ask is that how much demand in my data source there is, right? Or how many cars that I'm trying to deliver. And another question is that, okay, in my solution, how many cars I actually delivered, either on time or delayed, right? So you can use kind of human language to describe the question. And the model prompts here will includes, okay, I'll talk more in details in the live demo later, but it basically explains, okay, what does the model look like, what does my data source look like, and what is my supply chain graph look like, for example, right? So ideally, the AI agent should be able to kind of understand and reason about your question and generate code to pull numbers from your data source or solution file to answer your question accurately. Okay, so yeah, so basically those are the three type of questions that I just explained, and let me quit the slideshow and let me try to open my coding environment. Let's try to do some demo here. So okay, let me try to move this here. So here, yes,
real quick, there are some yellow lines on the screen. I don't know if they were marked.
Yes, I think somebody draws the lines there.
Oh, this is from the Zoom. Okay.
Yeah, it's from the Zoom. I don't know who from the audience that was playing with the marker.
Okay.
I was whoever is drawing these lines, please try to erase that if you can. Okay, so like I said, so I on the top part of the design graph, I implemented OR solver that which is in my OptModel file. This is a file has like 800 lines of code. I'm not going to explain it, but just let you know that I have this car production supply chain model that reads all of the inputs and build a model and try to solve them. Okay, and the source data in this data file, which is a collection of CSV files, and the output is stored in a different folder. Okay, let's suppose that we have already solved this problem, and what you can do in a different part is you can set up an agent, a code agent. This is the main kind of skeleton of my code agent. I can explain the most of the lines here. So here I'm using the Hugging Face framework, like I mentioned before, and we have this file, small agents, that provides a few functionalities. One of them is a class of code agent, and the other one is inference model. So in the inference model, I can specify, okay, which large language model I'm using. This one is actually one of the default inference models in Hugging Face, and you can also try DeepSeek or other things. By the way, one thing is the Hugging Face platform provides mostly open source models, so you wouldn't be able to find like Gemini or open AI models there. But those are actually, for my purpose, is powerful enough. And the same thing, similarly, in the previous like hands-on lab, you're generating these API keys. Here you have a Hugging Face token that's generated, and you have another like parameter called temperature. It's kind of a temperature that controls how creative you want your inference model to be. By setting it to 0.0, I can try to make sure that every time I'm producing the same outputs, if my input is the same. Okay, so the second part, the agent part, it's very easy to specify. Like I said, this agent is a code agent, so it does not produce strings, but it produces strings, but the string is actually Python code. And it can actually run this Python code in your environment. So here model, I'm using the first my inference model specified above, and secondly, code agent will have access of several tools, and each of these tools is actually a Python function you implemented. So you can provide more Python functions you wrote yourself, and the code agent will be able to call them when generating outputs. And also, we can allow the code agent itself to use several packages that are not already imported. And also, it will not try to use any arbitrary package, right? So if you have in that way, you can kind of make sure that your code agent does not do dramatically harmful things like deleting files from your file system. You're only allowing your code agent using several libraries here. And finally, here I implemented a simple command line tool that I can try to help myself ask questions and answer questions. Okay, so beyond that, what's another second important part? If you remember previously in the design, we have inputs, two kinds of inputs. One input is the user questions. Another part of the inputs is a model context string, which is nothing but a description of what my model look like, right? So here I have a paragraph that states that I have an optimization model solving a car production supply chain problem, And the supply chain consists of 12 nodes, and what are nodes? And I can tell, I can put the information that what does my data source look like, right? For example, the demand data is in this file, in CSV files, where each row indicates one specific car and what's the meaning of each column look like. And I can tell all of these informations to put all of these informations in human language in my model context string. And let's try to run a few instances here. So here I prepared 3 examples. The first example is essentially show the demand, or show the demand by parsing the input CSV files. So let me try to do that. So you can actually run this opt agent file because it's a CLI. I can put my question as a string there. I'm going to copy my, sorry, what?
Vinod has a question.
Oh,
Yeah,
go ahead.
I was super question. Oh, I'm echoing, but I'd also posted in the comment, but does the solver kind of maintain state when we repeatedly interrogate this? How is the setup? Or each time we instantiate the solver and like run it?
Does the solver maintain state to enable repeated interrogation? So no. The solver is a you can think of it's just a tool that if the agent decides to run the whole model to solve it again, it can. But you have to create a tool or create a Python function for the agent to use. So yeah, so okay. Let me try to copy this. Okay, so already start running, and the first part is actually exactly the model context that I provided, and also the question here is please compute the number of demand in my data source. And this is a very simple question. So it actually, it just takes one step. Oops, for some reason I copied it here. Okay, so the agent response is basically a dictionary that I know this answer is correct from the input data that the periods are from 61 to 74, and in each period the demand is about 2,000 cars to be delivered. And let me emphasize that this is not a kind of trivial question, because in the data it actually looks at a different form. So it's an input data is a data, well, it's a CSV file where each of the each of the row is one car in one period. So it does some aggregations here. And you can actually look at the code that the agent produced. And so that's the first part, examining the demand. And you can also try to examine the output. The second question here is, hey, just tell me how many cars you have successfully delivered in your plan. And in this call, it actually it needs to use several tools. So it's not a simple like CSV file parsing question. Oops, it produced a lot of Vings, but that's not important. So one of the so here in the first step, it actually produced 2 lines of code, and the first line of code is actually calling a tool that I provided to the agent. And the tool is to try to get all of the distinct car VIN IDs from the product group called car. So it understands what this tool can do, and it calls this this tool to get a list of strings, and this list of strings is actually used as an input in my second part of in my step 2. So step 2, it generates 15 lines of code, and here it uses another tool that inputs the output of the last step and to get solution flow. And the solution flow here is essentially a data frame in the format, and from that data frame you have to parse, okay, what is my assembly node, what is my delivery node, and if I want to figure out how many cars I'm delivering, I have to look at the flow between those two nodes specifically. I don't care about flows elsewhere, right? So and this part of the code does that exactly, and it was very beautiful. I was actually very surprised that it was very accurate. So although it's not a very straightforward question, and ultimately it produced a CSV file, and it produced the total number of cars fulfilled, which again I know this is the correct answer. Those are successes. Those are like parsing data and manipulating data and answer my questions. I have a third question that I set up to deliberately let the agent struggle. So I asked a very difficult question. The question is that, try to identify the bottlenecks. Okay, what does it mean by bottlenecks? I did not give very clear like this definition to the language model, right? But I told them I'm solving an optimization problem, and here's my solution, that we have like 28,000 of cars in demand, but in the solution we can only deliver about 26. Oops, there's a typo there. Okay. And that's really the reasoning part, that you need a model expert to kind of to figure out, okay, what does it mean by a bottleneck, right? So you'll see that it actually does a few things that tries to answer the problem, but ultimately it gets confused and stopped because I have a maximum of 10 steps. But it actually does a few steps of useful things. For example, it tried to extract the cars, and then it tries to understand, okay, what are the parts that are coming into the assembly node, and then do a few things, but ultimately cannot really solve the question of identify the bottleneck. I guess we'll see if next year it's kind of smart enough to reason about the model. And let me get back to the. I'm not going to wait for this to finish, but let me go back to my last slide. So yeah, so even this agent is pretty simple, and I think it's roughly about like 200 or 300 lines of code, including the model context prompt I provided to it. It's actually useful for me to write, for example, if I have this agent while I'm implementing this model or testing my model, I kind of get a chat GPT that knows what I'm doing, that knows what does the optimization model look like. So that I don't have to go back to the ChatGPT UI and rephrase every time what I'm trying to do, right? So that knowledge is already there in this code agent. And also another thought is that I'm not although I told the chat, I told this agent that what I'm trying to build on a kind of fairly high level, I did not tell the model the exact equations I'm modeling, right? For example, the inventory change equals flow in minus flow out for at each node, and there's a nuance of lead time of each transportation line, right? So those are standard kind of equations, but I did not say that in the prompt in a very verbose or tedious way. But I'm also curious that is that actually an efficient way of communicating with language models by using like words and prompts to codify the equations, because the equations is already in my code, and I can kind of. But anyway, that's one kind of thought that I have while working on this. Okay, and the final takeaways. What I'm trying to show here is that while writing down equations is great, it takes experience, it takes expertise, but it's in reality, it's only a small part of the successful deployment. In reality, in business, you are dealing with people, you have to explain your model, you have to understand every part of the data, right? And that area is where GenAI can really shine. For example, if you can build an agent and other people and other team, business owners can ask questions in plain English, that'll be much more scalable than you being a customer service and answering every questions, right? And obviously, industry is rapidly evolving. The language models like last month will be different from 3 months ago. So don't hold yourself back to experiments and try some agent in your workflow, right? Because while you're coding, you can write an agent that does something like this, and to try to streamline what you're doing. And sometimes agent can even like do some steps for you correctly, right? For example, in my previous demo, it actually produced a CSV file that were not there before. Yeah, so I think that's the end of my demo. Hopefully everyone is finding this useful, and I'm aiming to have my code in this demo as like a different zip file to send to you after the workshop. I hand over to Shubhangi for the last part.
Thank you, Hongbo. It was really awesome. Yeah, I enjoyed both the hands-on labs and the demo. Let me share. Hongbo, can you mute yourself? Yeah, thank you. Okay, so we have now reached at a very last part of the session. We have seen the theory, the practical with the hands-on and the demo. Now let's see where it takes us in our career. So So I'm going to talk about some of the emerging career and research pathways at the intersection of AI agents, operations research, and decision analytics. I like to call it as the golden triangle of convergence, where we have AI agents that provide autonomy and perception to sense the environment. We have operations research that provides a backbone, like we discussed earlier, and the decision analytics, which provides a full feedback loop for evaluating the outcome. So what are some of the career tracks at the intersection of these three fields? So the first and foremost is the research frontiers, where the most promising research area is the chips industry, where the research is bidirectional. What I mean by that is the research done in one is used in the other. So, for example, we have better chips for leveraging better chips for AI and OR related research to accelerate some of the intractable problems in complex computational area, especially the OR problems which were not solvable. They look promising now with the advent of the advancements in the better chips. The other direction in other side of that coin is the AI driven chip design. So how we can leverage the capabilities of AI and OR in automated layout and verification of next generation chips. The second track is the architect track, where the architects are designing sort of the brain of this AI agentic system. Some of the roles in this area are multi-agent systems engineer, where they design protocols for how fleets or robots or software agents communicate and negotiate, like Kiva robots in Amazon warehouses. The second one is the digital twin architect, where it builds high fidelity simulations of supply chains or factories where AI agents can be trained using OR models before real world deployment. And the third is we are seeing the smart operations research scientist, where instead of solving a static mathematical problem, you can build algorithms that re-optimize continuously as agents feed in new data. The third track is strategist. So in this track, we have directors and autonomous fleet managers who are strategizing where to use OR and agentic systems and when to where to place them, as well as where to have the human oversight. And then the third one is the algorithmic governance lead, where a compliance heavy role that audits automated decisions to ensure they aren't biased or creating systemic risk. For example, in automated algorithmic trading. And the last track is the translator track, where AI agents are running in the background, but and then they are providing advice on strategizing different outcomes. And the second role is the supply chain AI strategist, where we are strategizing, identifying where to inject agentic AI into a logistic network. For example, should we let the AI agent automatically reorder steel when prices drop, or just alert a human? So where to place the strategizing where to place these agentic AI agents versus human intervention. Of course, these are not this is not a comprehensive list, but these are some of the promising roles and tracks in this emerging field. Now that we have seen that this is a kind of golden triangle of three different skills, three different areas. So in expertise or specializing in just one is not going to be enough, and we are going to need a hybrid kind of skill stack with the foundation in all these three areas: OR, AI, and computer science and analytics. And with that, I think we are open to questions, if any. And thank you all for joining. It was a long session, but hopefully you enjoyed it and had some insights from it.
Does anyone have any quick questions? Or any quick feedback? Was that any immediate reactions?
Yeah, we'll definitely send the post session survey. It will help our chapter to grow better. This was brought to you by our Informs San Francisco chapter, and we intend to continue doing these kind of sessions and activities and bring AI and OR experts to you, all the members and Bay Area people.
Before we leave, like if you're okay, can we turn on camera? I want to take a screenshot just to kind of, this is our first event for the chapter this year. So just wanted to kind of document this if you're okay. All right.
And document all of people that made through 3 hours.
Yes. we are the real achievers. All right. Here we go. Okay. In 3, 2, 1. Big smiles is when, okay. Giving a second for when to, okay. All right.
Thank you.
All right. Okay. Yeah, I think I got it. But yeah, thank you, everyone.
That's all. Bye.
Thank you. Have a good weekend.
Thank you. Thank you.